Hi, in this video, I'm going to go through the AQA AS-level Chemistry paper. This is paper 2, and this is the second half of this paper. This is the 2021 paper. I did the first half in an earlier video. Okay, so the last of the long questions and then the multiple choice. Okay, last long questions. Define the term enthalpy change. The strict definition of enthalpy, and this comes up once every few years, is the energy change at constant pressure. So it's a pretty strict definition that a lot of people don't know. Right. Propane undergoes combustion according to that equation there. We've got bond enthalpy data there, and we have got the overall delta H, and we've got to use this to work out the bond energy value for the carbon single bond. Okay, so what I always do with these is draw a Hess's law cycle, and the third thing I put down at the bottom here are the gaseous atoms. Okay, so on the red arrow, we're going to be breaking bonds. Okay, and so that is going to be endothermic, so these are going to be positive values. What bonds are we breaking? Well, we're breaking two carbon-carbon bonds, and that's what we've got to find out. So let's call that X. That's 2X. We're breaking 8 carbon-hydrogen bonds, and they've got a value of 412. And we're breaking 5 oxygen-oxygen double bonds, they're 496. So if you add all that lot up together, you get 2X plus 5776 kilojoules. Okay, on the green arrow, we're going to make these bonds, okay? And so these are going to be negative values. Well, we're making 6 carbon oxygen double bond. So that's 6 times 743. And these are minus values because when they're exothermic, we're making the bonds. And we've got 8 of the oxygen hydrogen bonds, so that's 8 times minus 463. Add that lot up together, it comes to minus 8162. So what we're going to do now is we know that the blue value here, that is equal to follow the red arrow and follow the green arrow. So Hess's law. Okay, so we're going to get minus 246 for the blue, 2046. Is equal to 2X plus 5776 minus 8162. So let's get 2X by itself. So we're going to get there 2X is equal to minus 2046 plus, all right, this works out. So let's do it. Let's do it in 2 steps. So if we simplify that, we get minus 2046 is equal to 2X. Now that minus 8162 comes to plus, goes to minus 2550. So 2X is equal to 2550 minus 2046, which comes to 504. We divide by 2 to get X. X is equal to 252 kilojoules per mole. That is using this calculation, that is the value you get for the carbon-carbon mean bond enthalpy, 252 kilojoules per mole. It's got a positive value there because I think here we are actually breaking those bonds. Yeah, 252 is the answer. Okay, explain why the value given for the OO bond here, oxygen-oxygen double bond, is not a mean value. Well, it's because this bond only exists in an O2 molecule. So there's only one possible environment for that. So it is it's not a mean value over a range of compounds. Okay, onto the multiple choice now. Which alkene shows EZ isomerism? Okay, so I've color-coded in this. 2,3-dimethyl-butene is this thing here. Okay, now you can see on this carbon you've got the same things attached, same groups attached to it. So if you swap them around, it doesn't make any difference. There aren't two isomers, and it's also the same on that one as well. So that's not the answer. Can't show EZ isomerism. B, 4-methyl-pentoene. So I've numbered the red, and I've numbered the carbon atoms in blue, so you can see them there. Now you can see if you look at the two carbons there, this one has got two separate groups attached. It's got hydrogen, and then it's got this propyl group here, and this one has got a hydrogen and a methyl group. So if you swap those two around, you will end up with a different isomer. That one can show EZ isomerism. That's the answer. Let's just check. 3-methyl-propane, well, it's in blue here, and you've got two methyls on that carbon, so it doesn't matter if you swap them, and it's also got two hydrogens, so it doesn't matter if you swap them. And pent-1-ene in yellow, well, you've got two hydrogens on that carbon there, so you swap them about, makes no difference. Okay, so they give us the empirical formula, and we've got to work out the molecular formula. So if you got, this is by mass, so in 100 grams, let's say, you would have 40 grams of carbon, 6.7 grams of hydrogen, 53.3 of oxygen. We need to work out moles because we're not interested in masses. We want the ratio of moles. So moles, we're going to divide by the relative atomic mass. So that's going to be 40 over 12, 6.7 over 1, and 53.3 over 16. That gives us 3.3, 6.7, and 3.33. So then we divide by the smallest number we've got to simplify the ratio. And the smallest number we've got is 3.33. So we get 3.33 divided by itself is 1. 6.7 divided by that's 2, and that's 1. So the now the empirical formula is then going to be CH2O. Right, so it's going to be a molecular form, is going to be a multiple of that. They've all got two carbons, so that's going to be C2H4O2. C2H4O2, the answer is C. There's basically a mole calculation here. Driving a car, the legal limit for ethanol alcohol is 18 milligrams per 100 centimeters cubed of blood. What's this concentration in moles per decimeter cubed? Right, okay, so what is this? We need to convert this into grams first of all. So the mass of ethanol is equal to 0.08 grams. So now let's work out the moles of ethanol is mass over mR. So 0.08 over 46 for ethanol. That gives us 1.739 times 10 to the minus 3 moles. Okay, I need to work out moles per decimeter cubed. Well, so concentration, moles over volume. We've got 1.739 times 10 to the minus 3. And the volume is 100 centimeters cubed. So that's equal to 0.1 dm. That's over 0.1 dm. So that is going to standard form. The way they've done it is 7 times 10 to the minus 2. So that is going to be this one, B. Right. 12. Right. So this is free radical substitution, which is a propagation step in the chlorination of methane. Right. Now, hydrogen free radicals are not involved in this process, so that's wrong. Okay. And that's wrong because you've got hydrogen there as well. So they're both wrong on that count. C is a termination because you've got two free radicals coming together to not be a free radical anymore. That's a termination step. So it's got to be the last one, and it is because look, you get a methyl free radical and chlorine regenerates the chlorine free radical and you get your halo alkane. So D is the correct one there. 13. Which compound is not formed by reacting 3-bromo-3-methylhexane with warm ethanolic potassium hydroxide? So what's going to happen here? We're going to get an elimination reaction. We're going to eliminate HBr. Okay, so I've drawn 3-bromo-3-methylhexane down there in blue. Now, when you do elimination, you remove the bromine atom and hydrogen from the carbon next door. So if you remove that one, you get the double bond there, and that would be 3-methyl. It would be 3-methyl hex 3-ene. So that would be formed. Okay. Now, if instead of removing that green hydrogen there, you remove the bromine and this hydrogen, then you are going to get the double bond there, and that would be 3-methyl. That would be 4-methyl. Sorry. 1, 2, 3. I've drawn too many there, haven't I? Yeah, I've drawn too many. 1 minute. That shouldn't be there. Okay. So that green one, sorry, the green one is 3-methyl hex 2-ene. Yeah, so we get that one. The red one would be 3-methyl hex 3-ene. You get that one there. And then you could also, instead of removing those, you could also remove to a different color. You could remove the bromine there and a hydrogen from this carbon. And you get the double bond there, in which case you'd probably have to name it. So that would be carbon 1, 2, 3, 4, 5. It'd be pent 2-ene, and it's got this ethyl group on it on number 2. So 2-ethyl pent 2-ene, you would get that one, but you would not get B. You wouldn't get 3-methyl hex 1-ene. Okay, yeah, there's no way you're going to end up with a double bond between carbon atoms number 1 and 2, which is what you have there. That's not possible. Yeah. Okay, so these questions refer to the reaction of 1-bromopropane with potassium cyanide. So that's going to give us a nucleophilic substitution reaction. So we're going to have Cn minus, and that's going to go there and there. And so the product is going to be, we've lengthened the carbon chain. So it's not prop, it's but. So it's butane nitrile. That's what we have got, butane nitrile. These ones where you've got the amines are obviously wrong because you don't get amines, you get a nitrile. And C is wrong because you've lengthened the carbon chain. Right, which is the correct mechanism for the reaction? Right, so I've just written the mechanism, but this is wrong because the cyanide has a negative charge on it. There's no negative charge on it. This is right. That's delta positive. That lone pair will attack that carbon, and then the carbon bromine bond breaks. So that is the right one. Let's see what's wrong with this one. This one is, well, two things wrong. There's no negative charge on the cyanide, and it's the lone pair on the nitrogen which is attacking. It's not. It's the lone pair on the carbon that does it. And again, this one has only got one thing wrong. It's the nitrogen lone pair is attacking. That's not what happens. So B is the correct answer. 16. The reactions 1-bromopropane and 1-chloropropane with potassium cyanide occur at different rates. Which is the fastest? Well, this one is the fastest. And if you remember why, it's because the carbon-bromine double bond is weaker. And so it's easier to break. That's what it's got to break. The carbon-bromine double bond is weaker than the carbon-chlorine double bond. The reason why is because this is a longer bond. If the bond's longer, then it's going to be weaker. So the answer is 1 bromopropane, and it's because this bond is weaker. So A is our answer there. 17. Okay. Which compound has a different molecular formula? It's different from the others. Well, they've all got 4 carbons, so we rule that out. Now, what I would do now is look at the number of double bonds, because if there's no double bonds, the carbon to hydrogen ratio is going to be like that. If there's 1 double bond or one cyclic, because that reduces the number of hydrogens, then you're going to get CnH2n. If there's 2 double bonds, you're going to end up with a formula of CnH2n minus 2. Now, you can see that A is going to be like that because this has got 2 double bonds, and that's going to be different to all the other ones. So that's going to be CnH2n minus 2. Whereas B has got 1 double bond and 2 oxygens, obviously. So that's going to be CnH2n. C has got 2 oxygens, and it's got 1 cyclic thing, which reduces the number of hydrogens by 2. So that's CnH2n. And D has got 1 double bond as well, so that would also be CnH2n, and it's got 2 oxygens. So A is the answer there. A quick way of doing it. Right. 18. Which compound reacts with hydrogen bromide to give 2-bromo-3-methylbutane? So I've drawn that as the major product. Okay. Now, remember, when you form these compounds, I'm going to change this here and put the hydrogens down like this. What happens is you add HBr, so you add Br to one and H to the other. Now, that one, if the double bond was there, yeah, you would get that compound, okay? Because this carbon, if you think about it, that would be the one with the carbocation in it, in the mechanism. And that's a secondary carbocation, so that would be the major product. If the other one would be a minor, because if you've got hydrogen sticking to that carbon there, you'd end up with a carbocation on that carbon, and that would be a primary carbocation. So that is just go back again. That is the correct answer there. So we'd have a bromine here and a hydrogen there. They'd be added on. So that means the double bond would have been in that position. So you can see that is this bottom option here. Yeah, oh, that's what you've got. So you number those carbon atoms. You've got 1, 2, 3, 4, 1 double bond between 1 and 2, 3, and then 4, and you've got a methyl group coming off number 3 as well. So that is our correct option. 19. Which statement is not correct about the industrial production of ethanol from ethene? Okay. Right. The reaction is catalyzed by an acid. It is phosphoric acid. The reaction has 100% atom economy. Well, it does, because look, that's the only product that you make. You don't make any other products. An increase in temperature decreases the equilibrium yield of ethanol. That would be true, because this is an exothermic reaction, so high temperatures would favor going backwards. Right, and increase in pressure increase the value of Kc. Now that's wrong. The only thing that affects Kc is temperature. That's a bit of a trick question, right? What they're trying to get you think, if you increase the pressure, you can see that the position of the equilibrium would move to the right, so you would get more ethanol, because you've got 2 gas moles on the left and 1 on the right. So the equilibrium position would move to the right, but it would not affect the value of Kc. The only thing that affects the value of Kc is changing temperature. So they commonly try and catch you out with that by putting a reaction where, yes, the position of equilibrium changes, but Kc doesn't. 20. Which statement about the use of catalyst in a reversible reaction is correct? Right. The activation energy for the reverse reaction is increased. No, it's actually decreased in both directions. The equilibrium constant increases. It doesn't affect the value of the equilibrium constant. It just gets to equilibrium faster. The rate of the reverse reaction increases. That is true. Forward and backward reactions both increase. And the enthalpy change decreases. That's wrong. It doesn't. Catalysts don't affect the enthalpy change, do they? They just lower the activation energy. So C is the correct answer there. If you remember your classic sort of energy diagram from GCSE, where you have, your reactants, and so the products like that. Okay, and this would be the activation energy. Of course, this would be delta H, this yellow bit here, also not in yellow. That would be delta H for the reaction. And if you use a catalyst, well, what's going to happen is you will lower the activation energy, but look, you lower the activation energy, but delta H stays the same. Okay, so C is the correct answer there. Right, this is about rates of reaction. Okay, so an excess of magnesium reacts with HCl to form hydrogen gas. So the magnesium is in excess, so it's the moles of hydrochloric acid that is going to affect the volume of hydrogen produced. Line X on the graph shows the volume of hydrogen produced with time as magnesium reacts with 30 centimeters cubed of 1 molar hydrochloric acid. So how many moles of hydrochloric acid is that? That's conc times volume. So that's going to be 30, which is 0.03 dm cubed multiplied by 1 times 10 to the minus 3 moles of HCl. And that's going to control the moles of H2 gas. And the reaction is repeated using 20 centimeters cubed of 2 molar. So how many moles are we going to have there? Concentration times volume. So that's going to be 20 is, well, concentration is 2, and the volume is 20 centimeters cubed. That's 0.02. So that gives us sorry, that's times 1. That's not times 10 to the minus 2. So I'll just write it like that. 0.03. And this one here is going to give us 0.02. So we only got 2/3 the moles there. Okay. So that's going to give us 0.4, beg your pardon. Okay. So the answer then is going to be B. Okay, that's about 0.04 moles, isn't it? And that's 0.03 moles of acid. D would be if you use 0.02 and so on. And A would be if you use 0.06, okay, which we're not doing. So B is the answer there. And it would be a bit faster. Can you see that the line is a bit steeper with B here than it is with X? And that's because the acid is more concentrated, so the rate of reaction is faster. So that's going to be, that's 2 moles per decimeter cubed. It's only 1 mole per decimeter cubed with X. So the rate of reaction is faster. Okay, as well as where it levels out. Okay, and this is the last couple of questions. 22. Which statement is not correct about sulfur dioxide? It can be removed from car exhaust by catalytic converter. That's wrong. Okay, the catalytic converter removes nitrogen oxides like NO, NO2, N2O, and so on. It can be removed from power station flue gas by reaction with calcium oxide. That's true. It can cause respiratory problems, yeah, and it also causes acid rain. So A is the correct answer there. 23. What is the percentage atom economy for the production of ethanol from glucose? Right, so the MR of ethanol is 46. Carbon dioxide, the MR is 44. Right, so atom economy is equal to the mass of useful over the total mass of products multiplied by 100. Right, what's the mass of useful product? Well, we're going to make 2 moles of ethanol. So that's 2 times 46, which is 92 grams. Okay, that's going to be 92 grams of ethanol. And at the same time, we are going to make, right, we're going to make the 92 grams of ethanol there, but we're also going to make 2 moles of carbon dioxide. So that's going to be 2 times 44, that's 88 times 100. If you do that, you get 51.1. That is the answer there. Okay, and that is the last question on the paper.